Hi everyone, I'm Phil. I'm working off of slides that Dylan gave me, and I modified them a bit, so everything good about the slides is due to Dylan, and everything bad about the slides is due to me. So yeah, what is this work about? Very quickly, it's just about getting practical / efficient exploration algorithms in arbitrarily large spaces with nonlinear, like general function approximation. So the current understanding of RL theory is like there's a lot of statistically efficient algorithms with general function approximation, like the Bellman rank, bilinear, DEC, all these works. Most of them are intractable to implement, and the space of implementable efficient algorithms is much more restricted. So more or less you need some kind of linear transition structure if you want to get an implementable algorithm. So the goal for this talk is just to expand the scope of problems where we can actually perform both sample efficient and computationally efficient exploration, in particular like in nonlinear spaces with general function approximation. So quick background, I'm working in finite horizon MDPs. They're going to be reward free. Everyone knows how the dynamics for MDPs work. And we're going to look at reward-free exploration, which is you just want to find a single exploratory data set that can enable optimization of any downstream reward function. So concretely, you want to collect a data set that has good coverage so that you can run offline RL later for any reward function that's specified. So like I mentioned 2 slides ago, computationally efficient algorithms are mostly limited to tabular and low-rank structures. So what we're going to do here is we're going to generalize it to the setting of coverability. So coverability is a very elegant structural parameter for the MDPs. The definition of it is in terms of a coverage distribution mu that tries to cover all the occupancies in the MDP. So, okay, without the minimization, just the max pi, max xa, this is usually an assumption that we make about offline data distributions. It's somewhat necessary in order to do offline RL. For online RL, we just say there exists some distribution that could hypothetically help you do offline RL. And there's some nice examples where this thing is bounded. Like tabular MDPs, it's always bounded by the number of states. Block MDPs, like latent tabular MDPs, it's always bounded by the number of latent states. And in linear settings, it's bounded by the dimension. And the first observation here was that this actually enables sample efficiency just on its own. So there's 2 works that we know of, maybe more that I'm not aware of, where you can get sample efficient exploration under various function approximation conditions. So in particular under value function completeness and value function and weight function realizability, you can get sample efficient algorithms, but these are like, interesting statistically, but not implementable. There's these crazy, crazy confidence sets and optimization procedures to get optimism. And the starting point for this work, since we're going to do reward-free RL, is to notice that this mu distribution would be the perfect distribution to sample from if you wanted to do offline RL later, just by definition. And is it possible to find it, and can you do it efficiently? And there's a small problem that you might not be able to be realized as policies. You may not be able to collect data distributed from mu. So the first thing that we do is we slightly generalize this coverability definition to address these problems. So we define something that we call the L1 coverage objective. So if you have a policy mixture, P, which is just a collection of policies, and some approximation parameter epsilon, we define the L1 version of coverability in the following way. So the numerator, again, is just the occupancy for the policies. And in the denominator, you now have the occupancy distribution for your policy mixture. So how well does this policy mixture cover all the other policies? And the small plus epsilon in the denominator is just making sure that this thing is bounded. Is there any questions about this particular definition? So this has some relationship to, like in the low rank settings, these optimal design-based objectives. And again, in the offline case, this coincides with L1 concentrability, which is just a finer, more refined-grained version of the L infinity version. So the first thing to check is that this is actually sufficient for the reward-free problem, meaning that if you had a policy mixture that had this value for the L1 coverage, how would that affect downstream reward optimization? So this is just like a sanity check. This is just showing that if I collect data from the policy mixture P, I can optimize any downstream reward function up to the coefficient determined by L1 coverage, and then some small epsilon approximation parameter. So this implies, again, that if you just collect data from P, you can optimize any downstream reward function scaling with these two parameters. So this is only interesting if this value is actually small in given MDPs. So to look at that, we can check what the optimal value for L1 coverage is. So this is a parameter of the MDP. It's the best possible value you can get for L1 coverage by minimizing over the policy mixture. So if you knew the MDP, just sort of information theoretically, you could calculate the best policy mixture to minimize this coverage parameter. And that value is given by, we call it L1 coverability, written as COV. And we can compare with the L infinity version of coverability and show that, somewhat surprisingly, it's actually smaller than L infinity coverability. So, and in fact, this holds for all approximation parameters. So as an immediate corollary, this thing is still bounded for latent block MDPs and linear and low rank MDPs. Okay, so now I think we're going to talk about how can you actually use this thing to do exploration and reward-free RL. So the goal from now on, since this policy mixture is enough to do reward-free RL, we're just going to try to minimize the best value of P for the L1 coverage parameter in an unknown MDP. And we're going to use function approximation and, in particular, a model-based RL setup. So I'm going to give you a realizable model class, and I'm going to ask if you can solve for the best policy mixture. The algorithm itself is pretty simple. The way that it works is you're just going to find an estimator based on all the data I gave you. And then you're going to optimize the L1 coverage objective for that estimated model. And it's just a point estimate. There's just a single model that you get from like maximum likelihood, and you just optimize L1 coverage for that simulated model. And then you just roll out that policy mixture. So in pseudocode, the algorithm is called codex, coverage-driven exploration. Estimate the model based on the past historical data. Compute this, the best value for the L1 coverage parameter in that estimated model. So this is just a computational problem. And then just roll it out and start over. So this is efficient whenever you can do maximum likelihood over your set of models. And you can solve this planning problem in equation 1. And we're going to talk about how you can actually solve this planning problem in the sequel. But if you're happy assuming this as an oracle, we're done. This is efficient. Any questions? What is a policy cover? It's just a set of policies that tries to cover the space. Yeah. Sorry? Yes, it's a distribution of policies. Yes. So you sample one of the policies, you roll it out, and you just do this over and over. Mm-hmm. Yes. 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 So again, P is your policy mixture. If you collect data from the policy cover P, you can optimize any downstream reward function just via this decomposition. It's worst case in the sense that you can solve any reward function downstream, but that you could also do that as a pro. Like you don't have to specify the reward function. If the reward function is like, and in some sense, if the true reward function is very sparse, you're basically you have to do this anyway. So there's some subtleties. The L infinity version allows for arbitrary mu's in the denominator. It doesn't have to be realized by a set of policies. And in our definition, it's specifically made to be solved by a set of policies. I guess that's the main surprising component. Any other questions? Okay. Yes? Mm-hmm. Yes, correct. Why do? Yeah, we have a result in the paper. If you write this down for policy mixtures, this is just arbitrarily large. You need, if you write the L infinity version, but you just replace mu by policy mixtures. Yeah. Yeah. So that's what I was trying to say. If you write down something like this, but instead of an outside expectation, you just take the L infinity, this could be arbitrarily large even when it doesn't, like, that's, yeah, the mu version is not. Yeah. Okay. Good, cool. Okay, that was the algorithm. Here's just the sample complexity statement. It just says that you produce a policy cover that is within approximation factors O of the optimal coverage parameter. One salient feature of this is that you actually need all of the MDPs in the model class to have bounded coverability by coverability M star. You guys see the mouse? Yeah. This is assuming that you solve the optimization problem in equation 1 exactly. If you solve it up to multiplicative factor C, the C just shows up in the sample complexity. So it allows for like approximate optimization of this program. And if you're happy with these two oracle assumptions, this is the first efficient algorithm under this like coverability setting. Okay. So in the rest of this, I'll just talk about how you can actually implement an optimization procedure for this guy. So now the problem is, given a known NDP, can you solve for this thing? So there's no more statistics. It's just about how much computational costs you actually want to pay. So unfortunately, one caveat is that it doesn't quite reduce to a planning type procedure. If you just looked at the first equation, you'd say, oh, this is just planning. But the reward function itself depends on the policy. So it's quadratic instead of linear in the policies. And if you wrote it down for the special case of low rank, you end up with these like UCB type expressions, which we don't actually know how to implement very efficiently, like by reducing it to convex optimization. So one solution that we give is that instead of just optimizing it directly, you optimize upper bounds for it. And once again, the motivation here is that if you minimize an upper bound for the true parameter, that just shows up in the sample complexity. So this is just a computational gap that you're paying. The statistical cost is still the same. So the first relaxation that we give is called the L infinity relaxation. So if you assume access to a distribution mu that has bounded L infinity concentrability in the following way. So again, for tabular, you can just set it to be uniform. For block or low rank, there's similar closed forms. And since you know the model, you can actually just compute the closed forms directly. In general, there's an expression for the optimal mu. It's just proportional to the max visitation for any policy. And then the relaxation goes as follows. So the true coverability parameter is upper bounded by whatever coefficient you have for your mu times this alternate coverage parameter. And this one is much nicer. This one is actually just amenable to planning. So if you just had a planning routine, you could just call it on this fixed reward function, and you'd be done. So that's just, this pseudocode is just formalizing that idea. You just iteratively compute the max policy for this inner reward function. So if you just define this reward function, it's just a policy optimization thing. And this theorem is just showing that this works. There's a different extension. Yes, what's up? No, all of this is for known MDP. Yeah. Yeah. So in the algorithm, in the exploration algorithm, the optimization only happens on the simulated model. So whatever computation you want to do is all in the simulator. If you wanted to just brute force this, it would still be just in a simulator, no statistical cost. Okay. Yeah, what this works is so you set, at the top you said t is 1 over epsilon. The convergence rate of this thing is just log t times whatever the best is that you can do. Yes, exactly. Yes. Okay. Cool. There's a different relaxation that doesn't need knowledge of mu, but scales with a bigger coefficient. So this coefficient is called the push forward coverability. It's bigger than the other one. It's still bounded in the same way. So for tabular, it's bounded by x. For latent block MDP, it's bounded by s. For linear, it's bounded by d. But here, the relaxation, you can just compute this planning problem. And here, there's no special knowledge required other than the transition matrix, which you have because it's a known model. And this is the basis of another extension, which is just a model-free exploration algorithm. Instead of requiring a model class, you can just require value function and weight function realizability. And I'm not going to say anything else about this. So we implemented this on a very simple mountain car domain. There's 3 different baselines. The blue line is just the coverage algorithm. The green line is this maxent algorithm from 2019. And the orange line is just uniform random policy mixtures. We plot the number of unique states that you visit for each policy cover that you get. So over 20 epochs, you get 20 different policy covers. And then we're just plotting how many unique states each policy cover gets. There's a qualitative visualization of the heat maps for the occupancies. The white circle is just the starting state for mountain car. The black star, if you can see it, is the goal state. And in particular, the coverage algorithm is the only one that reaches the goal state. The planning subroutine, we just use reinforce. We just use the policy gradient algorithm, and it approximately solves this optimization problem. Cool. So then, just in conclusion, there's some immediate follow-up questions, which is just, does it actually work on like larger scale settings? Is there a more general approach for deriving relaxations if they are indeed necessary, like if the program is NP hard in general? And the sample complexity for this thing is it's a bit slow. Epsilon 6 is a bit slow. But usually, quote unquote, efficient algorithms have slower statistical rates. And then a broader question in general is just like, there seems to be a lot more hardness if you want to require computationally efficient RL. And can we understand that more formally? Like, what is the trade-offs? What is the broadest class of MDPs where you could do computationally efficient RL? Cool. Thank you. Yes, it's mostly just expectation. It's mostly just this expectation on the outside. This expectation makes it like just a planning or policy optimization problem. Cool. Yeah. Yes. The main reason it shows up, let me go to the pseudocode. The main reason it shows up is that you're doing MLE on past data. If you want to show that the policy cover is a good policy cover, in the current iteration, we do some like offline to online conversion. And if you only assume L1 coverability as a parameter, you have to pay some epsilon factors. If you assume L infinity as a coverage parameter, you actually get a faster rate. Yes. This is just saying like what's the different potential arguments that you could make under the structural assumptions. Yeah, so actually the flowchart's a bit different. You actually start with this epsilon. Like, what epsilon are you happy with here for your downstream optimization? So when you're doing reward-free RL, you pick your epsilon up front because it shows up as an approximation error term. And then then it gets fixed for the rest. So it gets fixed in the input to this algorithm, and then in the statistical rates. Yeah. Yes. Sure. We just discretized it. Yeah, and then just count-based estimation on top of that. Mm-hmm. guess it would depend on. Well, I guess so. In the low rank case, all of the occupancies are themselves linear. So then you could just parameterize them linearly and just try to learn them that way. I guess it would just depend on what, like the structure of the MVP. Yeah. Mm-hmm. Mm-hmm. Yes. No, it actually is. Yes, yes. Yeah. That's an interesting question if you can remove that. We thought about it a bit, but we're not sure. When does my slot end? I forgot. When does my slot? 3:15? Okay. I'm ahead of time. Good. Good. Thank you. Okay, final chance to ask questions about this. Oh, Noah, yeah. That's a great question. If there's any hope, wait, so which part are you asking about? It's not obvious. It's not obvious, no. It just boils down to whether or not you can solve the optimization problem efficiently or not. The way that the model-free algorithm works is you like inductively get a policy cover and just run policy gradient on on the weight function inside equation 2. So like you set this as a reward function, you just run like PSPD or something on that reward function. So as long as you had a fixed reward function on the inside, you're done. But if the reward function on the inside depends on pi, then you're kind of out of luck.